let's find for this function, f of xy is 5xy squared minus 4x squared y. And we're going to be looking at the point 1, 2. And we want to find the directional derivative. Or really, we should just say the derivative in the direction of. Well, that pen's trash. If there's a trash can here, I'd throw my pen at it, but there isn't. So for the vector u equal to, I'm going to do 5/13, 12/13. Now I'm going to point out, because they're going to come up often, there's probably 2 or 3 vectors that you might see frequently, which you should just recognize as being a unit vector. This is one of them. This is a unit vector. How do I know? Because I know this Pythagorean triple. So if you've seen a right triangle that has 3 integer sides, like the most famous one, the 3, 4, 5 triangle, or this like second most famous one, the 5, 12, 13 triangle, it is true that 5/13 and 12/13, they add up to, when you square them and add them, they add up to 1. Here's how I'm really thinking of this, just so you know. We know 12 squared plus 5 squared equals 13 squared, right? I mean, we do now if we didn't before. If we divide everything by 13 squared, look what we get. 12/13 squared plus 5/13 squared is 13 squared over 13 squared, which is 1. Oh, yeah, that's exactly that. So I'm just trying to make the point that you can certainly do the work to show that this is a unit vector, or you can just do the work where you divide by the magnitude. But I'm just trying to save you some time. If you can see that you have a 5/13 and a 12/13, or if you had a 3/5 and a -4/5, for example, you should get used to being like, oh, that's a unit vector. Because I know that when I square those and add them together, I'm going to get 1. Not everything you see is going to be right, but these are kind of like, aside from 0, 1, and 1, 0, these are the 2 other most like common unit vectors you're going to see. Okay, so anyway, let's find the directional derivative. So we're going to find 2 things. We're going to find the gradient. I personally do prefer this notation for evaluated at, but you can also write it as this. I'm not sure which way he is writing it. Either way is perfectly fine. Also, just a reminder, when you have a chance, fill out the attendance form. Don't worry about it right this moment. I mean, you can do it right this moment if you want. Either way, we're finding the gradient first. So I'm just finding the partial derivatives, fx, fy. And after I find those, I'm actually going to plug in the point 1, 2. So the partial with respect to x is going to be 5y squared minus 8xy. The partial with respect to y is going to be 10xy minus 4x squared. Right, this is a vector. It's just 1 entry here, 1 entry here. And then we're going to plug in the point 1, 2. So for my gradient, I'm going to get, and let's see, 5 times 2 squared is 20, minus 8 times 1 times 2 is 16. And then I'm going to get 10 times 1 times 2, also 20, minus 4 times 1 squared, which is just 4. So I get 4, 16. Sorry, I'm just noticing. All right, anyway, so sorry, I'm just looking at the handout I'm looking at. There's definitely some mistakes on the handout I'm looking at. All right, mistakes. So here's my gradient. And well, we'll talk about what this means in a minute. But for now, let's just do the calculation. So I'm going to take this and to find the directional derivative, I'm going to do the gradient dotted with that unit vector. That's just going to be 416 dotted with 5/13, 12/13. And honestly, I would rather not multiply 4 by 5/13 and 16 by 12/13. What I'd really rather do is factor out the denominator, meaning I would rather write this as 1/13 times the dot product of 4, 6, and 5, 12. You don't have to do that, but I feel like it makes it just a little bit easier. So it's going to be 1/13 times what? How do I dot those together again? What do I multiply together first? And then not 4 times 12, that is a 6. I think now I'm like, is that a 6? No, it's a 16. Apologies. Should be a 16. 16 times 12. So that's going to be 1/13 of 20 plus 16 times 12 is 192, I think. So that's going to be 212 over 13. And I doubt that reduces. You could maybe try. I don't think it reduces. It's very unlikely that reduces. But what we get here, right? This is, again, right? The whole idea is if this is your surface, and you're at this point on the surface, if you travel in this direction, the slope or the steepness of the direction you're traveling will be this steep, meaning if you go 1 unit in that direction, you're going to be going up 212/13. So it's going to be a lot of up for a little bit of over. That's what we're saying there. So you're going definitely up the surface, not down. So we could alternatively ask, I'm going to ask 2 more questions actually. Yeah. Sure. What's the directional derivative in the direction of, that seems like such a boring question to ask. Let's change it up. In the direction of v equal to 2, 3. So I should point out directional derivative still at the same point. 1, 2. So I'm at the same place on the surface. I'm just moving in a different direction, right? Instead of going, 5/13, 12/13, now I'm going 2, 3. Right, so still kind of pointing in the same direction. I would expect the slope to probably be pretty similar. I don't know exactly though. Or maybe I've got some really strange surface where things dramatically change when you move a little bit. I don't actually know. But I do know how to do the calculation. I still know my gradient. Hasn't changed at all. The gradient at 1, 2 is still 416. But now I'm going to find my directional derivative by doing 416 dotted with what? Well, it's not just 2, 3. It's 2, 3 as a unit vector. So I have to take that vector and divide by its magnitude. Or as I would rather write, multiply by 1 over its magnitude. That's what I really want to do. That's to me, that seems like the, oh, sorry, you guys can see that real well. To me, that seems like the easiest notation for writing that. So what's the magnitude of V? It's the square root of how much? And so the magnitude of the vector is just the square root of the sum of the squares of its components. So in this case, it's the square root of 2 squared plus 3 squared, which is the square root of 13. So for this particular problem, we're going to get the dot product, which is 4 times 2 plus 16 times 3 times 1 over the square root of 13, which is going to simplify a little bit. 48 plus 8 is 56, so we get 56 over root 13. Which doesn't feel, again, right, neither of these numbers feel particularly meaningful. But again, what I should point out is, right, this is like essentially your slope, right? If you were traveling in whatever, right, if you're traveling in that direction, you would be going up, right? Because your slope is positive. I want to ask one more question with this example because I know this typically comes up. Let's say we want to find, so pay attention to the phrasing here. I want to find the derivative at the same point. In the direction of the point. Let's be careful here. Sure. 3, 4. And the mistake people usually make with this sort of phrasing is thinking that that's the vector that we're going in the direction of. That's not the vector that we're going in the direction of. We're not going in the direction of the vector 3, 4. We're going in the direction that takes you from the point 1, 2 to the point 3, 4. So the vector, or direction vector, if you will, is, well, it's always the place you end up minus the place you started. So it's going to be the end point minus the beginning point. So they wrote it totally the wrong way. Wow, that's terrible. Why would I write the y coordinate first? Your end point minus your beginning point. That's the worst. Okay, thank you. Appreciate it. So the direction of travel is actually in the direction of the vector 2, 2. Now, it's tempting to say that the normalized or the unitized version of this vector is 1, 1. It's not 1, 1. The magnitude of the 1, 1 vector would be the square root of 2, which isn't 1. So just, I just want to point out, right? 1, 1 is not a unit vector. Neither is 2, 2. That's okay, we're going to fix it. So I want to find my directional derivative here. It's again going to be my gradient dotted with my direction vector divided by its magnitude. What's the magnitude of this vector? Yeah, square is my favorite number. Or if you prefer, 2 root 2. I do kind of prefer. Because we should try to simplify things if we can. So let's see, we're going to get, so you could even break this down just to 1, 1. Right, you cancel the 2 with the 2 there, but let's just do 4 times 2 plus 16 times 2 divided by 2 root 2 and get 8 plus 32, which is 40 over 2 root 2, which is 20. And I would probably not worry about rationalizing that, although you could and write it as 20 root 2 over 2. So you could, I guess you could rationalize this as 10 times the square root of 2. I don't really care about that. Someone might care though, so. Questions before we do that?
Why did you subtract 3 minus 1 and 4 minus 2?
So here's why. Because I was starting at the point 1, 2. and I was going in the direction of the point 3, 4. And so the vector that gets you from the starting point to the ending point is the vector 2, 2, because we have to go over 2 and up 2. So whenever you're given points to find the vector from the starting point to the ending point, you take your end point and you subtract off the beginning point. Always. So for example, if someone said something like, draw on paper, not that. If someone said, you know, you have some point A is 3, -2, and some point B is 4, 5. The vector AB that starts at A and ends at B is 4 - 3, 5 - -2. That's the vector that gets you from that point to that point, which makes sense, right? Because to get from 3 to 4, you have to add 1. To get from -2 to 5, you have to add 7. So just be aware, right? Sometimes they like to phrase those questions as, so there's a difference, right? There's find the directional derivative in the direction of this vector. Great, that's your vector, divide by its magnitude, dot product, whatever. Or there's find the directional derivative in the direction of this point. And then you have to find the derivative from your starting point to the ending point, and then that's the vector you're going to use. Slightly different. Not terrible, just right. It can, you have to be aware of the phrasing. Good question. Other questions? Or we're getting more examples. Let's look at this next example. And let's actually, yeah. So I want to say that right now. I kind of do. Yeah. Let's look at, sorry, I'm just trying to think of something. Yeah, let's do, sure. I kind of want to go back to this other example. So, let's look at this. Let's say our function is 1 plus 2x times the square root of y. And at the point 3, 4, we want to find the derivative in the direction of, sure, let's make it fun. Let's do 12 -9, which is definitely not a unit vector, but we should know how to normalize it without too much terribleness. So let's first find the gradient. And then we're going to talk about what the gradient really is. So a gradient is a vector of partial derivatives. It's going to be, let's see, the partial with respect to x is going to be just the square root of y. And the partial with respect to y is going to be 2 times x times the derivative of the square root of y is 1/2 times y to the -1/2. If you want to make this look a little nicer, you can say it's the square root of y and then x divided by the square root of y. There's my gradient for any point x, y. Questions about that? Yeah. Would it be? Did I make a mistake? I might have made a mistake. I make mistakes, right? You should ask the questions because let's see, I did. I told you, right? The derivative of x is 1, but the derivative of 2x is 2 times 1. Yeah, there's definitely a 2 there. I saw some concerned looking faces. I'm like, I don't think I did anything wrong, but clearly I did. So don't hesitate. I might sound confident. I make mistakes easily. So even if I sound like this is totally right, don't hesitate to ask. I really obviously might have made a small error. It happens. So that's the gradient anyway, right? At any point x, y, that's what your gradient is. So again, which we might not have really talked about the meaning of the gradient. We're almost there. What's the gradient at this particular point? Well, let's plug it in and find out. It's going to be 2 times the square root of 4, and then 3 divided by the square root of 4, which is going to be 2 times 2, 3/2. Yeah, we'll come back. And then specifically, if I want to find the gradient, sorry, the directional derivative in the direction of that vector, it's going to be my gradient dotted with that vector divided by that vector's magnitude. And everyone should get used to being able to look at those two numbers and telling me what the magnitude of that vector is. What favorite unlucky number is the magnitude of that vector? 13 for sure. 12, 5, 13 triangle. The magnitude of that vector is 13. You could also do the work, right? You don't have to just know it, but it's going to save you time to know it because it's going to come up more often than you would believe. But it is also true, oh yeah, the square root of 12 squared plus -5 squared is the magnitude of that vector. And that's going to be equal to the square root of 144 plus 25, which is the square root of 169, which is definitely 13. It is really 13. And then, let's see, 4 times 12 is 48. Why am I writing it like that? That's not right. I don't get a vector anymore. So I'm writing the wrong thing, right? When I do the dot product of two vectors, I don't get a vector anymore. I get a number. 4 times 12 plus 3/2 times -5, all divided by 13, which is not lovely because I got fractions and fractions. But I'm going to get, let's see, 48 minus 15 over 2, all over 13, blah. I might rewrite that as 96 over 2 minus 15 over 2, all times 1/13. And that's going to be 81 over 26. The numbers are not beautiful here. They rarely are in this class. All right, so let me ask you a different question. Paper. So for this particular function, way up there, for f of xy equal to 1 plus 2x times the square root of y, in what direction is the derivative the greatest? Good question. I should say, in what direction is the derivative at the point 3, 4? Right, because different points would certainly have different answers to this question. But if we look at one point, there should be one direction that has the greatest slope. Or if you think about it this way, right, if you're climbing on this, sorry, if you're like hiking on the side of a mountain, there's definitely one direction that is the steepest direction to go, right? Straight towards the top. Whereas other directions are like, oh, I'm just doing the nice like switchback, right? Maybe I'm going downwards, but there's only ever one choice for which direction has the steepest incline. Well, what is it? Well, here's how we find it. I want to maximize. Don't worry, we're not going to have to actually maximize the directional derivative. So here's the hard way to do it would be to be like, okay, well, I know my gradient is 4 3/2, and I want to do the dot product of I don't know what divided by its own magnitude. That seems terrible. I don't want to do that calculation. This is where it's really important to remember that we have another way of finding the dot product of two vectors. So I'm going to remind everybody, one way of finding the dot product of two vectors, right? Because this is again just the gradient of f dotted with u divided by the magnitude of u. Well, another way to find the dot product of two vectors is to remember it's the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So I want to make this as big as possible. The gradient is what it is, right? The gradient is, okay, I just said it, I'm saying something. The gradient is what it is, right? Whatever we have found the gradient to be this. So the magnitude of the gradient is some number. This doesn't change. Right? Because we were asked what direction gives you the steepest slope. Well, let me ask everybody. Everybody should be able to tell me the answer to this question. What's the magnitude of this vector that's already divided by its own magnitude? 1, right? It's a unit vector. Its magnitude is 1. Okay, so this doesn't change. This is always 1 because it's always a unit vector. So the only way to guarantee that this is as big as possible is to make cosine of theta as big as possible. And this is the biggest it can be when the angle is, what angle makes cosine the biggest? I know cosine of pi over 3 is 1/2. I know cosine of pi over 6 is the square root of 3 over 2. But what's the angle that makes cosine the biggest? Or better question, because we don't actually care what we do care. What's the biggest cosine can be? Right, 1. The biggest cosine can be is 1, and that's going to be when theta is the angle of good old 0. So you get the biggest value for the derivative, for the directional derivative, when the angle between the gradient and the direction is 0. Or in other words, you get the biggest directional derivative when you're in the direction of the gradient. Let me say that again. You get the biggest directional derivative when you're in the direction of the gradient, meaning the gradient is the direction of steepest incline or of maximal increase or whatever you want to call it. So when someone says, like, if back to the hill, if you're on the hill and you want to know what direction is the steepest up, I should say. It's the direction of the gradient. So the way I would phrase this is the gradient vector points in the direction of steepest increase or maximal increase or largest positive, whatever you want to call it. Always true. Kind of cool. It has so the gradient really has some meaning, right? It's not just like this thing actually is like, oh yeah. So if you're looking at like a contour map, you guys know what the contour map is, like when the maps have all like the little lines on it. The lines all represent like the same amount of change in height. And the closer those lines are together, the steeper the slope, because you have a greater gradient. You're crossing more lines when you're traveling in that particular direction. So that's one kind of idea to think of. It's not a great example, but it's a good idea. Back to this question here. If I want to know the direction that maximizes the directional derivative, well, it is the direction of the gradient. So here's not quite the right answer. The answer is not just what the gradient is. The answer is the gradient divided by its own magnitude. So the gradient divided by the magnitude of the gradient is the direction of steepest incline. And some people are not super particular about saying a direction vector has to be a unit vector, but I feel like the teacher might be particular about that. So I would caution you to err on the side of direction vectors should be unit vectors. Always take that vector and divide by its magnitude. Okay. Yeah. The other cool thing, math cool. The other interesting thing is that we can also ask the question, what is the steepest slope? Well, we know the direction has to be the direction of the gradients. So you can say, well, if I'm going to calculate this, I'm going to get, I could do it the old way, the more normal way, where I'm doing the gradient vector dotted with the unit vector normalized, or I should say the vector normalized to be unit vector. But again, if we look at the other way of doing it, think of it as the magnitude of the gradient times the magnitude of this unit vector times cosine of the angle. We already know the answer. What's the biggest this can be? Well, we already know this is 1. And what's the biggest cosine of theta can be? It's okay. Don't worry about it. It's really okay. What's the biggest? Sorry, you guys can't see that. What's the biggest cosine of theta can be? Yeah, also 1. So the biggest this can be is the magnitude of the gradient. So the steepest slope is the magnitude of the gradient, and it occurs in the direction of the gradient. And the particular example we were just doing, the steepest slope, or the maximal rate of change, or whatever you want to call it, is the magnitude of the gradient vector, which was, I think, 4,3. Yeah. Which would be the square root of 4 squared plus 3/2 squared, which I guess we could calculate. 16 plus 9/4, that's going to be 16 is 64/4 plus 9/4. So you get square root of 73 over 2, or the square root of 73/4, but I would rather say the square root of 4 is 2. So the nice thing here is that if you ever asked for what's the direction of steepest increase, or like some people like to phrase it like here, well, here's actually here. Let me just write that instead of like saying some people like do this. Let's just do one. You got a skier. Skier maybe has 2 eyes. I don't know. On a slope, wants to get down the mountain as fast as possible. If the surface is modeled by f of x, y equal to, let me put something out that's not too terrible. Oh, yep, of course. X cubed plus 2x squared y squared minus y cubed. And our skier, is at x, y equal to, well, let's make it kind of fun, 2, -1. What direction should they travel in? All right, so if I wanted to climb as quickly as possible, which would be hard, right? On skis, climbing as quickly as possible is hard. You don't usually want to go up the steepest direction. But if you did want to go up as fast as possible in the steepest direction, you go in the direction of the gradient. So if you want to go down as fast as possible, turn around. Right? If our surface, not that our surface looked, right? If our surface looked like that, and we were trying to go up as fast as possible, we would just go the opposite direction to go down as fast as possible. So the direction of steepest increase is the gradient. The direction of steepest decline is the negative of the gradient. That's what we're going to find. So my gradient is not lovely. It's going to be the derivative, partial derivative with respect to x, which is going to be 3x squared plus 4xy squared. And the partial with respect to y is going to be 4x squared y minus 3y squared. So at our point, at 2, -1, we're going to get the vector 3 times 4 plus 4 times 2 times -1 squared. And the second coordinate is going to be 4 times 4 times -1 minus 3 times -1 squared. So I end up with the vector, let's see, 12 plus 8 is 20. -16 minus 3 is -19. And that's almost the right. So if I didn't have, like, if this was a test question, I didn't have a lot of time, I might leave my answer as that. I might say, well, the direction is clearly 20 ahead and 19 to the whichever direction, 19 to the right. Sorry, 19 to the left. I was pointing to my right, your left, right? If you're thinking about the X, Y, Z coordinate system, right? 20, -19 would be 20 that way, 19 that way. But really, if I'm asking for the direction I should travel, well, actually, so that's the wrong direction, right? That's the direction of steepest increase. So my actual answer should be, sorry, I forgot the question. That's why it's always good to go back and read the question. Oh, yeah, we want the direction of steepest decrease. We're trying to go down the hill. So my actual answer should be the negative of the gradient. And we should also really divide by the magnitude of the gradient. Which never feels like a good time when the numbers are big, but it's not too bad. That's going to be negative this vector times 1 over the magnitude, which is the square root of 20 squared plus -19 squared. And honestly, the only thing I might do after that is distribute the minus sign and say it's -20, 19 times 1 over that number there. I don't think there's anything really to be gained by multiplying those out. You can, it's not particularly necessary though. So that's the direction that's going to get you down the slope as fast as possible, at least at that point. Time is it? Okay, we got time. Cool. Before I keep going, are there questions about this or about things in general? Yeah. Sure. So let me draw a better picture. Actually, sorry, let me think for just 1 second. So the reason for the negative is the gradient is the direction of steepest increase. So if you go in the direction of the gradient, you're going up the surface, assuming unless your gradient is 0, which it almost never is. So you're going up the surface. On the other hand, if I want to go down the surface as fast as possible, I'm going to go in the opposite direction of the gradient. That's why I'm putting the negative there, to give me the opposite direction. If the gradient happens to be 0, meaning the 0 vector, right? Because so I really want to kind of get it stuck in your heads The gradient is a vector. Say it again. The gradient is a vector. So if the gradient is 0, what I mean when I say the gradient is 0 is I mean it's the 0 vector. 0, 0. And if the gradient is the 0 vector, well, what does that mean? It means that there's really kind of no direction of steepest increase, right? Because the 0 vector is a kind of a direction. It's really, the 0 vector is like a point. You're not really going in any specific direction. If your vector is 0, if your gradient is 0, it means no matter what direction you travel in, you're not going to be increasing or decreasing really. It really means you're probably at a local maximum or a local minimum. You're probably at the bottom of some surface or at the top of some surface. For example, my favorite example, our mountain. Which looks like this. So my gradient is negative 2x, negative 2y. And what's the gradient at the point 0, 0? It's the 0 vector. Meaning if you're here, there is no direction of steepest increase or steepest decrease. Because any way you go, at least at that one particular point, the amount of increase or decrease is 0. I know, like after you get off that point, then you start decreasing. But at that point, right? If you're thinking of just that one instant there, there's no increase or decrease, no matter which of the directions in 360 degrees you travel. And it's true if you have a local maximum. It's also true if you have a local minimum. That point that right there at the bottom of that paraboloid would also have a gradient of 0. I know it's steep in any direction you would travel, but at that point you're at the bottom. So there is, right, you've got a flat tangent plane. Right here, the tangent plane would be parallel to the xy plane, and here the tangent plane would be parallel to the xy plane. And there's no up or down when your tangent plane is like this. So really, when you're finding the gradient, you're also kind of finding the slope of the tangent plane. Kind of interesting. Yeah. The reason I mention this is because I've seen this kind of question come up before where someone asks you, like, what does it mean if the gradient's the 0 vector? And you're like, oh, well, it means this stuff. And I can do more to show that. Can you show the page with the steepest slope, please? Of course. This one here, the skiing one, or the previous one? Maybe this one. This one? Okay. Yeah, we could do that. We could do an example. Yeah. Yeah, that's probably worthwhile. Sure. So we're going to look at kind of a long-ish example, but I think, yeah, it's worth our time. Okay, I'm gonna. But that was enough there. That's a lot of writing that I don't want to do. Let's do it anyway. So let's look at an infectious disease model. Okay. But that was enough. You might be wondering, well, why does this matter? I feel like people ask that question a lot in math classes, but I feel like in this series more than others, right? There's a lot more application, and we kind of see things. We do some examples that I think are actually reasonable. Like we're like, oh yeah, this seems like you could actually use the math in a real way. So why would a directional derivative of a surface really be important for like modeling, like, because I mean a lot of this is like kind of meant to be like health sciences and that kind of thing. How does it kind of relate? Well, here's one example that is actually kind of cool. Let's say so let's label some things. R naught is the average number of new infections that an infected person causes. When put into a completely susceptible population. It's a lot of writing. I will point out that all of this is already written down in Grant's notes. If you didn't want to write it all down, you don't have to. Okay. And then it's going to equal 5 times 1 minus V times D over 1 plus D, where D is the number of days the person remains in the population while infectious. And V is the fraction of the population that's vaccinated. And so just to think about this, let's see if this equation even kind of makes any sort of sense. So the number of new infections depends on the vaccine rate and the number of days. And you would think that the higher vaccine rate should mean less infections. All right, that tracks, right? Because if V is a number that's closer to 100% or 1, this is going to be smaller, which means the whole thing will be smaller. And the more number of days, the more infections we should get, which is also true, right? Because if D, the larger D gets, the larger this fraction does get. For example, if D was 1 day, this fraction would be 1/2. If D was 9 days, this fraction would be 9/10, which is a lot bigger than 1/2. So just want to, it's not a bad idea when these things actually represent real life situations or models. It's good to think about, like, does the thing even make sense? And yeah, it does. It makes sense that the higher vaccine rate would mean a lower number of new infections, and that more days spent in the population would mean a higher number of infections. So, first of all, what would the average number of new infections be if we had, say, someone in the population for 2 days and a vaccine rate of 10% or 0.1? So we're writing our percents as decimals. Well, that's going to be 5 times 1 minus 0.1 times 2 over 1 plus 2, which is going to be 5 times 0.9 is 4.5 times 2/3. That's going to be 9 over 3, which is 3. So if someone remains in this population for 2 days, we would expect 3 new infections on average. It's interesting, I think, and maybe this is just a feature of something the model is lacking. It doesn't actually care at all how big the population is. And this could be a population of 100 people or 1 million people, right? That piece of information isn't captured in this model. Maybe that's just not a very good model, or maybe it doesn't actually really matter. I don't know. So here's what we want to talk about. And I'm just going to read this part because it's a lot of words to write. Suppose public health officials are considering a reallocation of resources that will increase the vaccination rate, but comes at the cost of increasing the number of days that an infection person might be in the population. I don't know why that actually makes sense. Like, why would increasing the vaccination rate mean that someone might stay in the population longer? I don't know. But we're trying to make a question where we actually have to, like, do something that makes sense. So we're really asking the question, how much can we increase V and decrease D? Sorry, yeah, and increase. And have an overall effect of decreasing or not, because that's the goal. The idea here being that we only have resources to do one thing. So if we increase the vaccine rate, we can't also decrease the number of days that someone's in the population, or vice versa. We're trying to decrease the number of days someone's in the population, we can't also increase the vaccine rate. Yeah, so yeah, so let me read this again just to make sure I'm saying it the right way. So suppose public health officials are considering a reallocation of resources that will increase V that comes at the cost of increasing D. Yeah, so we are increasing both. One of them is what we want, and one of them is what we have is the result of, right? You don't get both things you want, right? You can either do a good thing for V and a bad thing for D, or vice versa. So we're saying, well, we want to increase the vaccine rate because that's something we have control over, but it's coming at the cost, and I don't know exactly why, but it's coming because we want the problem to make sense. Is really why. It's coming at the cost of, well, if we take the time, spend the resources to increase the vaccine rate, we're going to end up having people in the population for longer. Maybe it's not a great example, but it's what we're doing. The net effect of any reallocation of resources thus depends on how much the reallocation increases V and D. So how does this have anything to do with what we're doing? Well, we have to make an assumption. So here's the assumption we're going to make. Suppose any reallocation results in D increasing twice as much as V. Remember, we want V to increase. We don't want D to increase. So the question is, does it even make sense? Like, so we can kind of do both. We could increase. We could have basically essentially V go up by 1 and D go up by 2. Maybe that'd be great, but maybe it would actually be better to have V go down by 1. And 1's probably not the best number here because 1's 100%. Maybe let's say 0.1, 0.2, so the numbers are not stupid. Essentially, we can allocate the resources anyway. We can allocate the resources where we would get more vaccination, and then as a result, have people in the population for more days. Or we can spend the resources to decrease the number of days, but that would also end up decrease. We wouldn't have as much to spend on vaccinating people. Okay. So here's the idea. We're going to use a directional derivative. And like how? Well, here's how. So we have this equation. R naught of dV is still the same as it was before. And here's what we want to find. We want to find the rate of change of R naught, right? We're trying to increase or decrease this. Good question. We want to decrease it, right? So we want to find the rate of change of R naught and decrease it. But what direction do we have to be traveling in? So here's the thing. We are traveling in we're traveling in the direction where every increase in the vaccination rate leads to twice the increase in the number of days. So we're traveling in the direction of, we didn't really say which of their, I guess D is the first variable, V is the second variable. So we're traveling in the direction of 2, 1. Right? For every one more vaccine number, we get twice as many days. Because of what we're saying right here. But really, I should divide by the magnitude. So really, I should have that. Are there questions before we get really into the calculations here? Calculations aren't going to be that bad, but I just want to make sure there aren't any questions. So here's the way I would like you to think about this. This function is a function of 2 variables. It's a surface. And we're somewhere on this surface, right? We're at the point where, well, specifically, we were looking at this point here. You guys can't see what I'm looking at. We're looking at this point here, right? The one we did before, where D was equal to 2 and V was equal to 0.1. So we're at some point on the surface and we would like to know if we go in this direction or the reverse direction, which of those directions is going to decrease our rate of our amount, which direction is going to give us the biggest negative rate of change. Okay, so we're going to find the directional derivative. You might be saying, James, we've only got one direction. Well, just bear with me for a second. So, come on. We need to find our partials because we're going to find the gradient. So the gradient of this R naught is going to be the partial with respect to D of R naught and the partial of with respect to V R naught, which looks kind of messy. Also, I didn't write V here. I wrote 5 for some reason. Sorry, that's not right. That looked weird. The second piece of this feels much easier. The partial with respect to V is just going to be, I might even write this out. Let's give ourselves some more room. You can see that, right? So if I've got partial with respect to V is just going to be 5 times -1 times D over 1 plus D, or negative 5D over 1 plus D. The partial with respect to D is a little bit uglier, so we're going to have to use the quotient rule. So the constant 5 times 1 minus V hangs out, and we're going to multiply by quotient, so it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That does simplify. 1 plus D minus D is just 1. 1 plus D squared. Looks like we've got 5 times 1 minus V over 1 plus D squared. So there's my gradient in general. And then we're going to evaluate the gradient at the given point. Okay, so if we plug in the point, and again, we were at D equals 2 and V equals 0.1. Not a very high vaccination rate. We'd probably like to see that increase. Let's plug it in and see what we get. I'm going to get, let's see, 5 times 0.9 over 1 plus 2, so 3 squared. And then here I'm going to get negative 5D, so negative 5 times 2 over 1 plus 2. That's looking like, what's 0.9 divided by 9? I think it's going to be 0.1, right? So 5 times 0.1 should be a 0.5. And here I have negative 10 over 3. I guess I probably wouldn't, well, no, it's fine. I mean, decimals and fractions seems very probably right. It's 1/2 and negative 10/3, but okay. So there's our gradient. There's the direction of maximal increase, which would not be the direction we wanted, right? We would, if they asked us how should we change things if we could like get what we wanted, we'd be like, oh well, I want to go in the opposite direction of this and decrease the number of days by 0.5 for every increase of the vaccination rate by 10/3. That would be ideal if I could have that. It's not what I get, but it's what we would want. So to get what we actually get, we're going to take our directional derivative. And we're going to say, okay, that's going to be the gradient dotted with the vector u. And we already had the vector u. I know it's been a while since we saw the vector u. The vector u was this guy right here, right? The direction we were given, we didn't get to choose, divided by its magnitude. So we're going to have 1/2, -10/3, dotted with 2, 1 divided by the square root of 5. That's going to be 1/2 times 2 plus -10/3 times 1, all times 1/√5. So it's going to be, okay, 3/3 minus 10/3 is -7/3 times 1/√5. So -7/3√5. So let me ask you all a question. Did our R naught, which was our infection rate, number of new infections on average, did what we want to happen? Is this good news? It is good news, right? Because the rate of change is negative. Right? The directional derivative is negative, meaning the infection rate is decreasing if we travel in this direction. Meaning, so if we increase vaccinations by some number and also increase the number of days by twice that number, that has an overall net positive result. We are going to have a decrease in the infection rate, even though we are increasing the number of days of exposure. It's kind of a long example, but I think it does make the point that, yeah, there is some actual real possible world application to this very kind of seemingly geometric idea, right? Where you're in 3 dimensions, you're on a surface and you're like, well, what direction are you traveling in with the steepest increase? Well, here's an idea where like you have a function of multiple variables. You're like, if we can think about what direction this is going to decrease in the most, or is it going to decrease in the direction we're given, we would like to know. Okay. Come on. Yeah, that's not super necessary. Let's go on to the next topic. Well, I mean, the next topic is very related. I feel like there was something else I wanted to say about directional derivatives. I'm just going to repeat myself one more time because I think it's important. Gradient divided by its magnitude, direction of steepest increase. Wow, that's not how you spell steepest. Or if you prefer, direction of maximal rate of change. And then the gradient itself, its magnitude, is the maximum rate of change. Or if you prefer the maximum rate of change, or slope, or incline. However you want to say those things. And then we're going to use this stuff to find maximum and minimum values of a function. So we can use this to find where a function of multiple variables has a maximum or a minimum or even a saddle point. So the thing to take away, and I shouldn't try and draw pictures when there are lovely pictures right here for me. The whole idea here is that whether we have a maximum, a minimum, or a saddle, at the point where you have a max or minimum recital, the tangent plane is parallel to the xy plane, or is horizontal if you want to use those words. That's the whole idea, is that at any one of these points, you don't have any change, right? If you traveled in the direction on that particular plane, you would just keep staying at the same level, and you wouldn't go down, you wouldn't go up. So at any critical point, the tangent plane has to be horizontal, meaning both partials are going to be 0. Or in other words, the gradient's going to be the 0 vector. And I don't think we've talked about this before, but it's definitely, so most other calculus classes, when they talk about multivariable derivatives and stuff, and they talk about finding a maximum or minimum of the surface, they just talk about it in the context of finding where each partial is 0. But we know that the partials make up the gradient. So critical points, just like in 17a, we find critical points by setting the derivative equal to 0, and then or undefined. Critical points are where the gradient is equal to the 0 vector. Or alternatively, where each partial derivative is equal to 0. And there are 3 kinds of critical points. There are maxes, there are minimums, and there are saddle points. A saddle point I really think of as a maximum in one direction and a minimum in the other direction. So if you're thinking about a saddle, which is called a saddle because it literally looks like a saddle, right? Like saddle you put on a horse, or also when you're out, there's a lot of hiking examples. We talk about 3-dimensional calculus. If you're out hiking in the mountains, you know, like you hike up to this one little point, and then you can either go over the hill or you can kind of go up that way. That's a saddle as well. So let me draw it. I like drawing saddles. It's like the only thing I used to be kind of good at drawing. So let's say James is going up the mountain. Oh, yep, I'm going up, 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 up. And I get to this point right here, and I can either go over the other side or I can continue up this way to the summit. That's a saddle point because it's a relative maximum in this direction. It's a relative minimum in that direction. And here's kind of, I mean, there's a couple of different ways you can draw this. I'm a fan of drawing it like that personally. It's kind of a neat thing. Obviously, I can only draw so much of it because it goes on forever. That's kind of the idea. There's your saddle. And it definitely has a maximum one direction and minimum in another direction. Whereas an actual relative maximum or relative minimum is those things in all directions, right? If you have a relative maximum, it's the maximum no matter what direction you approach that. And if you have a relative minimum, it's a minimum no matter what direction you approach it from. Saddles are kind of interesting. Sorry, Kate, see that. So let's look at an example. Let's find, and we'll also talk about classifying all relative or local, same thing, extrema for the following function. Xy is x squared plus y squared minus 2x plus 4y plus 3. So let's find our critical points. I'm really just going to find where the gradient is 0. The gradient is, let's see, the partial with respect to x is 2x minus 2. The partial with respect to y is 2y plus 4. And if I set that equal to 0, 0, What's the only coordinate I get? Well, x has to be 1, and what does y have to be? Yeah. So there's our only critical point. Now the question is it a maximum, is it a minimum, or is it a saddle point? And that's where we have to do a little bit more work. Do we have time? Yeah, we have time. Yeah, we have time for that too. We do the thing. Oops, that's all right. Sorry, 1 second. Okay. Sure, we'll get there in a minute. So here's how we tell if we have a maximum, minimum, or a saddle. We calculate this thing. It's called D. It's really the determinant of the Hessian matrix, which is not a thing you need to remember, but it is what it is. The easy way to calculate it is to know that D is equal to the product of the second partial with respect to x times the second partial with respect to y minus the square of the mixed partial. But I will point out, since we know about matrices and their determinants, this is really equal to the determinant of this matrix. The determinant of the matrix of second partials. In the first row, you have the partial with respect to x. In the second row, you have the partial with respect to y. And then the first column, you have the partial with respect to x. And the second column, you have the partial with respect to y. It's not a big deal. If you never remember this ever in your whole life, you'd be fine. But since you guys know about determinants, I feel like it's worth saying that. So we're going to calculate this. All right, here's my function. Yeah, we got time. We got time. I can do it. Where'd my function go? Oh, right there. So my function was this: x squared plus y squared minus 2x plus 4y plus 3. fx was 2x minus 2, and fxx is 2. Fy was 2y plus 4, and fyy is 2. And what's fxy? Big old 0. What's fyx? Also big old 0. They should be the same, which is why we don't write fxy times fyx, even though that would actually be what you have in the determinant, because fxy times fyx is really the same as fxy times fxy, because as far as we are concerned, any function, we're going to see the mixed partial is the same either way you take it. Not always true, but always true as far as we're concerned. So here, our determinant of the Hessian is going to be 2 times 2 minus 0 squared, which is 4. So here's what that means for us. If this value is positive, which it is, it means we either have a maximum or a minimum. And to tell if it's a max or a min, you look at the one of the second derivatives. In either case here, both of my second derivatives are positive or negative. Positive, right? If the second derivative is positive, which way are we concave? Concave up or concave down? Concave up. Positive is concave up, and which means we have a max or a min. Gotta have a minimum if it's concave up. So if this is positive, it means you have a max or a min. And we know it's a max in this case. Sorry, we know it's not a maximum in this case. We know it's a minimum in this case because either second derivative is positive. You don't have to check both because they will be the same. And I will tell you that if this value is something that is negative, then you have a saddle. And I will also point out that this particular function is just an upward opening paraboloid. That's what it looks like. So there's your minimum value right there. Kind of cool. Not that interesting, but kind of cool.